Hi, my name is Lorcan Conlon and I'm a PhD student at the ANU, and this is my poster presentation for this year's CQC2T Workshop. Today I'm going to be briefly discussing how well multiple parameters can be estimated simultaneously. So to begin, I'll just briefly describe what we mean by a quantum measurement. So in order to measure something, we need to first prepare some quantum state rho, and this quantum state rho then will pass through a channel which depends on a parameter theta that we want to learn about. So as the state passes through the channel, it picks up information about theta, and when we then measure the state, we can get information about theta from the measurement results and produce an estimate of theta hat. And the difference between our estimate theta hat and the true value theta basically tells you how good your measurement strategy is doing. And by using things like entangled probe states or squeeze states, this measurement can actually be improved. And another way you can improve your measurement precision is by picking the actual measurement strategy appropriately. So the ultimate limits in quantum measurements are given by the high-level bound. But in order to actually reach the high-level bound, we're required to perform a collective measurement on infinitely many copies of the probe state simultaneously. So what this means in practice is you have to receive your probe states one by one, store them all in a quantum memory, and only after you've received all of your states can you then measure them all simultaneously. Now obviously this is exceptionally difficult to do in practice, and nobody has been able to demonstrate this yet. So a bound on single copy or two copy precision, something that's much more feasible, would be very useful. And this is basically what our work does. We introduced a new bound, which is a bound on separable measurement precisions. So this applies when you can only measure your probe state one by one. As an example, we apply this to qubit rotations. So we take the maximally entangled 2-qubit state, rotate one arm of the state about all three axes of the Bloch sphere, then we decohere the state, and then we try and measure the three rotation parameters. And what we found was that in order to measure all three rotation parameters simultaneously, you don't actually need to use collective measurements. Separable measurements get you very, very close to the high-level bound. And so our work sort of introduces an experimentally relevant bound, and it introduces finite size effects to quantum metrology. Thank you for your attention, and please feel free to ask any questions.